So in the next few minutes, what I'm going to talk about is about durable executions and diving deeper into what is a durable execution, why does it matter, how do you achieve that. So before we dive into that, right, let's just talk a little bit about applications and the states. Right? If you are writing applications, one thing you would probably realize is that in the end, when you look at your application and the application code, your applications are basically state machines. Because they are maintaining some state. Let's say even if you are retrieving a user information and then finding the email and sending out an email, you just have 3 steps here, right? And then they are kind of chained together in a sequence, but things get more complicated. Also, when you think about state, there's a notion of an application state and a business state. Oftentimes, what happens is the business state talks about various high-level state that a business is interested in, whether you have sent an email to a user or not, whether the user has responded or not. But to send an email, you have to have few more steps done. Similarly, to check whether user has opened the email or not, again, you have some more steps. Those are essentially your application states, right? In the end, it's a superset of business state, you can some way do a mapping from N to 1 or there. And where application state kind of comes into picture is, it's a state of your application code, right? In the end, like the code that you're writing or using some configuration as a code, whichever way. It also talks about how you order your execution, in which order it gets executed, how you handle retries and failures and all of those things. And really what happens when that failure happens, what do you do with the failure cases and so forth. So I want to put down one hypothesis here, right, which is that when you think about application flows, they require durability. And why do we need durability? When you look at your flows, usually application flows are complex. If you go back and look at your code for some of the use cases that you have built, you will realize that there's a lot of code there, handling exceptions, try catch, different business cases, and so forth. One of the things is that when you think about failures, we often, when you start writing code, we start with the happy path and then we start adding edge cases and failure cases, right? And failures are usually not exceptions. They are typically norms. Things are going to happen. If you run an application long enough or large enough in terms of the scale, the failures are going to happen. And this is where kind of complexity kind of builds up, right? How do you handle those things? What happens when you have built out an application flow where you have gone almost to the end and something fails? Now, what do you do with that abandoned transaction? Do you do a rollback? But it could be a very long running transaction. It could be a completely distributed state of your application where you don't really have a notion of a database transaction. So how do you handle those things? What if you have to kind of continue where it failed, right? Who is maintaining all of those things? So it starts to get a lot more complex. And even if you think about it, that if everything is still in a monolithic environment, it's not completely distributed, this can still be complex enough because your transactions may not be that fast or may not be very small enough that you can maintain using a database, and then you still end up with the same set of challenges. And this is why it becomes important that your flows have a durability. And when it comes to durability, what I mean here is your state is preserved at every step of the execution, and therefore if the application fails, the underlying hardware has a failure, it can pick up where it left off and continue and complete. Meaning that once you start an application flow, it is guaranteed to complete, either in a failure state or a completion state, but in a terminal state. So to illustrate this further, right, let's think about an order processing flow. Right? Let's say you are building an application that does order processing. Here's a very pseudo Python code here, right? What you are doing here is you are doing some validation. If there are no validation errors, you are calculating some tax information. Maybe you are calling a service that does a tax calculation. Maybe it's a library. Most of the time there's a database behind the scenes that if you give a zip code and a county, it will give you tax information. It's complex enough that it requires its own service. Then you are generating some sort of invoice, right? Putting together the base price, the quantity, tax, and shipping information, everything. And then you are sending a confirmation email to the user, either via an SMS or sending an email or something, and then you wait. You wait for the order to be fulfilled. Maybe it's an e-commerce order, and then now you have to wait until you get information from the warehouse that no, it has been shipped now, here is a tracking ID and so forth, and then you notify the user. Very straightforward. And if something bad happens, or if the validation fails, you send back an error response saying that no, hey, something wrong with your order. Maybe by the time you placed an order, the inventory was already out of stock, so you should retry, or the price has changed and you should relocate and whatever not. But now let's think about it, right? Maybe your text calculation service is down. It's maybe database is undergoing maintenance, and something bad happened and it took longer than expected. You are trying to send an SMS. Let's say you are using a third-party service to send out an SMS, right? You don't want to build your infrastructure to send an SMS, and they have rate limits. So you can only send so many SMS. But your service is very popular now. It's Christmas time, and there's a lot more orders. You are getting product. You don't want to lose messages. You want to preserve them and retry so that eventually it lands. But that can happen. And we didn't talk about how do you wait for fulfillment, right? Because that can take minutes, hours, days, who knows what, right? Depending upon the inventory. Maybe item is completely back ordered and needs to be, actually manufactured before it can be fulfilled. It can take days for it to happen. So you have to wait now. You're not going to keep your head waiting for days here, right? That's not even physical. So where starts to happen is that now you have to start thinking about that. Every step in the process you need to be able to persist. Not everything is something that can be restarted every time. So once I send a confirmation email, and if my process dies, I should continue my waiting for the order fulfillment as opposed to starting from the beginning or just abandoning the transaction altogether. So this is why durability becomes important. But at the same time, when you think about application durability, right, durable code execution, it's very similar to saying that when you choose a database, the database should support ACID transactions or support durability, right? Yes, it has to be absolutely there, which means that any framework that you choose, anytime you build an application that requires durability, this is a table stakes. This is like 101, and it has to be there. And what also means that every function call has to be persisted somewhere, so that it can be retried, replayed. If it is rate limited, it can wait, and it can wait for a longer period of time without blocking your threads and so forth. But more importantly, if I call the process order function, it must guarantee it completes at the end. So if we say that durability is table stakes, then what do we need? What else is there that you need to think about when you build applications? Like, one, if things fail, why did it fail? You want the visibility into it. Maybe it's a permanent error, zip code was invalid, and you should just completely abandon the transaction, roll back, give a user an error message back. Maybe it was a transient error and you should retry, and you don't want to retry immediately, probably not going to resolve it. You need to have some sort of retry loop that has decent amount of backoff and things like that to be able to handle that. If there is a rate limiting that is happening, you want to wait until you get your turn in the rate limit queue and then continue forward. So that's one more thing that you need to kind of think about and build it. And more importantly, once it goes to production, how do you debug those things? Like when something fails, oftentimes what we kind of resort to is, we look at the logs to see what's going on. We try to put some sort of context, and we take a pen and paper and try to draw it and say this is what happened, right? Or look at the ID, try to kind of match it with the code, and try to do some sort of correlation. But can we make it easier, right? Do you have tooling and platform that offers that kind of stuff? Not only that, beyond debugging, what happens if you have extremely large parallel execution happening? That makes it more complex because these forks can be running on multiple machines, if not tens, maybe hundreds of machines. Where you go and check what's happening where, right? Things could be running in a loop with sub processes and child workflows. Like, how are you going to kind of keep sense of all of those things? So it gets more and more complex. So again, yeah, durability is table stakes, and then the most dreadful question comes is, when somebody asks, like, please explain to me how this whole thing works. Like, can you document this? I personally don't writing documentation. Nobody loves documentation. And documentation, we know one thing: you write documentation, and then you write the code, and the moment your code goes to production, your documentation is obsolete because you have made so many changes. The documentation doesn't make sense anymore. Also, your things will change. By the time you roll out on a processing flow, you're already working on version 2. You have to kind of maintain those things. So it becomes more and more critical for the code to become self-documenting. So somebody can look at it and say, oh, this is how everything is, as opposed to trying to explain somebody or put it in a control state somewhere. Other thing is the versioning. Things are changing all the time. You are experimenting with new features, and this could be either new technology, a new way of kind of fulfilling the business requirements. Not everything is ready to go to production. You want to do some sort of A/B test. Maybe you want to do canary testing because you are not sure like how the new process or the new functions or the systems are going to behave. So you want to do versioning, and this is where how do you do versioning, right? Typical approach is you write a new function, put a v2, and then you have v3, and you have a whole bunch of codes with different v's, and you don't even know who's using what function. And then we all know, right? We start sending out emails asking people to see, hey, who's using this version? I am going to deprecate this, and then nobody responds until you deprecate, and then you have to kind of roll back and everything. So when you think about durable code frameworks, right? This is where you don't want to roll your own, right? It's easy to kind of try to put together things using out of the box tooling that you can find. But most important thing is you want to have a platform that brings the execution durability. Durable code execution platforms have recently kind of been the talk of the architectural patterns. They offer guaranteed execution, and essentially they implement the code orchestration as a design pattern, and lets you focus on the business implementation. This is the most critical piece, right? As engineers, as developers, our job is to kind of how do we every minute that we spend writing code, that code has to move the business forward as opposed to trying to solve in nuts and bolts. So how do we kind of focus on that one? So this is why choosing the right platform becomes important. And of course, not every framework is equal, right? The question that you want to ask when you are thinking about durable code execution is, can I debug, can I monitor my production flows at scale? If it is one execution, yeah, fine, maybe you can look at the logs and correlate. What if I've got 1 million executions running every day and 2 of them fail? Can I find in a few seconds exactly which 2 failed and why it failed? And can I rerun them with a click of a button or a simple API call or a call in my SDK? Is it framework and language agnostic? And this is important, right? You have invested probably years worth of time in writing code, libraries that are being used. Now, if you want to throw everything away and write a new one or implement a new framework, the switching cost of frameworks and libraries is expensive. They will also introduce new bugs. So, can you write things instead of kind of rewriting everything? Can you reuse stuff that you have with little changes or maybe some wrappers so that you can directly put things into production that you already have tested over the years. Every if condition has a meaning there, right? That you don't want to kind of rebuild and retest everything. And more importantly, can you build really complex workflows? Like when I say complex, I mean the workflows that has hundreds of tasks. Maybe thousands of parallel executions happening, loops, switches, and everything. And now imagine trying to monitor and debug those things in production. So those are some of the things that you want to think about when you think about choosing the right platform for durable execution. And again, durability is table stakes, right? What comes after durability is what really is going to make a difference. And of course, there are also some anti-patterns, right? These are some of the things that we have learned over the years. One is you don't want to implement versioning in the code. The moment you put things in code, it's definitely going to incur technical debt sooner or later. And it also makes it very difficult to upgrade the flows in production later on because you have very little way of looking at the dependencies. Because if your dependencies are across different code bases, across different teams, you are now resorting to like code searches and trying to figure out who's using what context and whatever not. Other thing is, oftentimes what happens is we try to end up implementing everything as an HTTP endpoint through a microservices-based architecture. That also introduces complexity because by breaking down things into different HTTP services or microservices, you have essentially broken down monolith. But the moment you write code to orchestrate them, what you have done essentially is you have built a distributed model. Now you have code that is understanding of different code, microservices, they are calling each other, and you essentially have a spaghetti. And you don't even need endpoints all the time, because sometimes the only purpose they serve is to be called through another orchestration layer. So there might be better way of doing things like service workers, which are better in terms of handling back pressure, in terms of handling rate limits, and a lot more lightweight when it comes to infrastructure and some of the security aspects. And more importantly, when you think about resiliency parameters, right? Resiliency parameters are essentially the ones which defines the behavior of your code when things go wrong, when things fail, when you are rate limited. If you were to start implementing those things in your code, imagine the amount of code that you have to write just so that you can make that call to do text calculation. Now you have to look at, like, did I get a rate limit? If so, I should wait, and how long should I wait? If it failed, should I retry? And what if that thing has to change? Like, who's going to go and change the code? So, abstracting those away and keeping your code simple as possible is the key, rather than making your code more complex. And more importantly, when you're writing tasks, you want them to be written as stateless services. And this is a very important thing, because if you think about stateless piece of code, functions or services, they are much easier to reason with, because they take exactly a very well-defined input, they process the input and produce an output, and it's easy to write the test. If they are stateless or has very less set of dependencies, when you have a larger workload, you can scale them out. So scaling up is pretty trivial. But the moment they start encoding the application state, now you have to also think about state, and that makes complex. Scaling stateless services is much easier than scaling stateful services. So these are some of the anti-patterns that I would love to share with you. And so this is where Conductor essentially plays a role. Right? Conductor was built to solve these problems, mainly around how do we build a platform that allows developers to focus on writing code that drives the business forward, as opposed to focusing on nuts and bolts and infrastructure. And the way it works essentially is Conductor acts as an orchestration layer that can orchestrate across your code base, and this code base could be anywhere from legacy monolith to serverless, humans, and everything in between, right? And in today's world, some of it is also Gen AI. And essentially what it does is, it lets you define your process flow or the code execution graph separately, and uses the event-driven architecture to execute those tasks and puts the durability into them. So you are not worried, and you are not thinking about how do you build durability into your code. That comes out of the box. So let's take a look at the exact same thing that we talked about earlier, but how would I build using Conductor? So this is the same code, and as you can see, right, like it's not very different from what you see earlier, except that instead of directly calling the functions, it is using a workflow to orchestrate functions. We are creating a workflow, putting all the tasks in a sequence. This can of course get a lot more complex, but for the sake of brevity and simplicity here, I'm putting everything as a sequential execution. But I have a wait task here that waits for fulfillment, which means that I don't have to have a thread wait or anything here. As you can see, I'm not persisting anything in a database here myself. System takes care of it, and my workflow is kind of ready to go. This is production ready code. This will handle failures, it will handle rate limits, it can wait for days, months, years, whatever it takes to fulfill the order. And the amount of code that you write is no more than what you write earlier. As a matter of fact, if you think about all the resiliency part of it, all the durability part of it, you are going to end up writing much less code. So that's the end of my presentation. Happy to take more questions, but if you want to kind of play around with Conductor, you can go to play.orkes.io. It's a playground. Conductor is an open source based open source project, so take a look at the GitHub repo, and if you love it, give it a star. And where Orkes comes into picture is essentially it takes the open source and gives you the cloud hosted version of it with things that enterprise would need, right? Things like availability and so forth. Yeah, sorry.
The example you showed is like pretty straightforward, which is like it's a sequential thing.
Yeah.
But in real life, it's not that simple. It's
Yes.
more like spaghetti, like what you're saying. Like
Yeah.
Microservices depending on microservices.
Yeah.
So how is Conductor going to help in that?
So Conductor essentially allows you to define workflows that are complex, right? So it gives you the same level of programming operators that you would find in languages, right? So you can put conditional logic, parallel executions, fork joins with parallel executions, or the loops so that you can run things in sequence. So essentially, if you can write the code, the same thing can run in Conductor as well. So the real world examples, as you say, right, gets really complex. We have some examples that probably will not even fit in the screen because they have like 300, 400 tasks inside it.
Yeah, I can relate to this because I was at the clinical trials company for like 2 years, and we had a microservices architecture, and we had like 18 microservices, and they were all linked with each other.
Yes.
Like A is B depend on B, B is depend on C, C is depend on A. So it's become so complex that it's like we had a terrible time trying to debug and get things done.
Yeah, and I think the advantage with something like Conductor is that your microservices just remains independent. They don't know about the existence of each other. Somebody else is wiring up, so the spaghetti kind of unravels into more like one-to-one calls. So you go from n square to just O(n) complexity when it comes to the wiring things together. And because your dependencies are centralized, you know exactly what the sequence is, and you can replace it much more confidently because you know exactly what's going to happen. And again, as I said, you don't always need microservice either. Yeah. This could be service workers, and that simplifies infrastructure overall as well.
Does it also require that microservices should be designed in such a way that this is possible?
Sorry?
Yeah, the microservice should be designed in a way that we can make use of this. I mean,
not really. It's like when we built Conductor, for example, we already had heavily invested in microservices, so it just runs out of the box. And essentially, Conductor works in it supports two kind of microservices, right? You have microservices that are exposed over HTTPS endpoints, so it directly makes a call. Or you write service worker where you take your function, wrap it around, in my previous example for, I would just create a function and wrap it around with a Conductor task, and it will expose itself as a microservice talking to the server. Yeah.
Viren, if I can chime in with our experiences that, you don't want that dependency between the services because you described it as the distributed monolith, right?
Yes.
Which is kind of a problem. But what I like about it is that the control of the flow of the now application of the orchestration is all handled by Conductor. You have a console that tells you this particular process failed, right? And based on the logic in your workflow, you may have said, skip it, this is not critical, or stop and abandon, abort the whole process. So you're going to know. They also have some retries that if you're trying to connect to HTTP, maybe it was just a network issue. So you can afford to retry. Or sometimes it's like, well, this is a very atomic transaction. You want to stop it if nothing happened. So all that logic, what I like about it is that you can build the control flow in Orkes or in Conductor, and you really focus your team and your value added into creating the most efficient individual task at a time, right? And we, for example, have to send potentially thousands of documents. The same document, IQVIA, I know IQVIA, we work with IQVIA, right, in the clinical trials industry. You know that you have to distribute a single document or hundreds of documents to all the sites.
Yeah.
So in our case, some of the workflows are just very repetitive. But if there was one document that failed to deliver, that's a big problem because you need to guarantee that all the sites in research sites in our industry receive the document. So this is very critical. Or you could have very complex workflows that are not repetitive, but it allows that dynamic tasks and you don't have to define them. You just literally like in a for loop, right?
Yeah.
You can generate all that from here.
Thank you.
So you mentioned integration with like Bedrock or large language models in general. Like, what are some of the ideas that you have, or some of the thoughts you have on integration with that? Because it's kind of inherently non-deterministic. So, you know, there's got to be some challenges with you saying,
yes,
this flow has to execute, and then you work with an LLM that may not agree.
I agree, and this is where, like, I think what we have seen is there are two kinds of use cases, right? There are like fully autonomous, or where you can use LLMs, and you know, it's more kind of where you can, you know, let me kind of rewind this a little bit, right? So there are kind of two patterns here, right? One is where you can look at the output of an LLM and write some logic to determine whether, like, you know, it has the right output or not. And this can be done through kind of clever prompt engineering. For example, when you're using RAG, my prompts usually tell me that, like, you know, if you do not understand the question, or if you cannot find the context in which that I'm providing from the vector database, please answer with a specific string saying I do not know, or something like that. And then my workflow can look at the answer of the LLM and make a determination whether, like, you know, I got the answer or not. So that is one thing. Second is where it's critical to kind of make sure that, like, somebody as a human looks at the output before moving forward. So what we did was, like, you know, we combined them with humans in the loop. So you have a task that kind of calls a language model, takes the output, sends it to assigns to a human, and then somebody looks at it to validate whether this makes sense or not. And this is important, especially if you are in regulated industries, dealing with financial information, or just dealing with the customers, right? You don't want to let your, you know, AI chatbot lose on customers, because, you know, those things are constantly changing and you don't know what it's going to produce as an output. So these are some of the patterns that kind of are emerging, where, like, you know, you are essentially using LLMs as a co-pilot for humans to be more productive. Yeah.
Very cool. Viren, in our case, we did a POC with the LLM models. And in the simplest of the cases is, I want to create a template for a prompt. And if you're connecting to the API, you need to write a little bit of code. It's not a big deal. But if I want to change to another model because I want to try it, these guys made it very easy that you just exchange the task, or maybe you parallelize them, or you just change the configuration. So you don't have to write infrastructure code. To me, that's so important, and it's so simple that it adds a lot of value.
I think the other thing that we are seeing is parallelizing calls to different LLM models. Like, you know, you would use two different providers with the same prompt or similar prompt, and then look at the output and, like, use some algorithm to determine which one is better, and then use that. Awesome.
Thank you.
Thank you.
Thank you.